if W is 4.52 plus minus 0.02, X is 2 plus minus 0.2, Y is 3 plus minus 0.6, then we need to calculate Z is equal to X plus Y minus W and its uncertainty. So Z is equal to X plus Y minus W, X is 2, Y is 3 and W is 4.5. So Z is equal to 0.5. Here we are neglecting the second digit of the measurement because it is up to 1 decimal point. And its uncertainty delta Z is equal to delta X plus delta Y plus delta W, and it is equal to 0.8 centimeter. So with the average error we can calculate Z is equal to 0.5 plus minus 0.8 centimeter. But if we are taking the standard deviation, then we need to calculate delta X square plus delta Y square plus delta Z square square root, then it is equal to 0.6. Note that we round the uncertainty to one significant figure and round the answer to match with the physical quantity of the measurement. Next example is if X is equal to 2 plus minus 0.2 and Y is 3 plus minus 0.6, find Z. Z is equal to X minus 2Y and its uncertainty. So we can easily calculate Z is equal to X minus 2Y. Central value of the X is 2 and Y is 3. So 2 minus 2 into 3 is minus 4. And second one is its uncertainty, delta Z is equal to delta X plus 2 into delta Y. Delta X is 2, delta Y is 0.6, 0.6 into 2 is 1.2, so delta Z is 1.4 centimeter. So with the average error, Z value is minus 4 plus minus 1.4, but with the standard deviation it gives us 0.9. So we need to keep the same number of significant figure as that of question to match our answer with the numerical problem. Next is if the one quantity is a multiplication of two quantities or the division of two quantities. Suppose Z is equal to X into Y or Z is equal to X upon Y, then we can easily find out the error involved in the measurement by taking the percentage error. So the final formula is delta Z upon Z is equal to delta X upon X plus delta Y upon Y up to so on. So if there is X, Y, Z or number of times how many physical quantities are there, depending upon that we can easily sum up all the relative measurement or percentage uncertainty with the measurement. So delta Z upon Z is equal to delta X upon X plus delta Y upon Y up to so on. Whether there is multiplication or division of two physical quantity, there is always some involved in the measurement of error. Next, the same rule holds here. If we are taking the simple average error, then delta Z upon Z is equal to delta X upon X plus delta Y upon Y up to so on. But if instead of average error we are using the standard deviation or the values or the X and Y physical quantity, they are not correlated with each other, then we can easily find out the standard deviation. It is a simple formula, delta Z upon Z is equal to delta X upon X whole square plus delta Y upon Y whole square up to so on and its square root. It is also we can easily calculate by taking the square of the first quantity, a relative uncertainty or the percentage uncertainty in the first quantity, its whole square plus a relative uncertainty in the second physical quantity whole square up to so on, and then taking the square root of that physical quantity. Next one is example related with this. So then W is equal to 4.52 plus minus 0.02 centimeter, X is 2 plus minus 0.2 centimeter. Then find Z, Z is equal to W into X, and we need to calculate its uncertainty. So the average, simply we can calculate Z is equal to W into X. W is 4.52 and X is 2, its central value. So Z is equal to 9.04 centimeter square. Next is average error. Average error, if we are taking the error to be the average, then delta Z upon Z is equal to delta X upon X plus delta W upon W. So first one is delta W upon W. Delta W is 0.02 and W is 4.52 plus delta X is 0.2 and X is 2. So delta Z upon Z is equal to delta W upon W plus delta X upon X, and it is equal to 0.1044. So delta Z is equal to Z into 0.1044, it is equal to 0.9. So with the average error, it is equal to 9 plus minus 0.9, but with the standard deviation it is also approximately equal 0.9. So Z physical quantity is equal to 9 with an uncertainty of 0.9 here. Next is, if we are taking the physical quantity Z is the fraction or the division of two physical quantity X and Y with the dimension of velocity. So X is in centimeter and Y is in second. So the central value of the X is 2, while its error is 0.2, and the central value of Y is 3, and the error involved in the measurement of Y is 0.6, then Z is equal to X upon Y, and it is equal to 2 upon 3, 0.6667. The number of figures we want, we can write like here. We want only up to 1 decimal, then it is equal to 0.7. So if we are taking the average error, then delta Z upon Z is equal to the error involved here, it is 0.6667, then it is equal to 0.2, but with the standard deviation it is equal to 0.15. So the last one is, if we are taking any physical quantity which is equal to the exponents of some power, so with the simple average error we can easily calculate delta Z upon Z is equal to, the exponent should come in the front, so m delta X upon X plus n delta Y upon Y, but with the standard deviation we need to write delta Z upon Z is equal to m delta X upon X whole square plus n delta Y upon Y whole square up to so on. So this is one example for this. Z is equal to WY square upon A raised to power half. So then delta Z upon Z is equal to delta W upon W plus 2 into delta Y upon Y plus half into delta A upon A. So with this thing we can calculate delta Z upon 28.638, it is equal to 0.49. So delta Z is equal to, multiplying these two, 0.49 and 28.638, it is equal to, up to round off, it is equal to 14 centimeter square. So Z is equal to 29 plus minus 14 for the average error, and it is equal to 29 plus minus 12 for the standard deviation. Next example is if z is equal to wx plus y square, then we need to calculate the uncertainty involved here. So first we need to calculate for wx and y square, then we can easily sum up all these. So delta z is equal to delta v plus delta of y square. So first we need to calculate delta v and then we will calculate delta of y square. So v is equal to wx. With the help of this we can calculate delta w upon w plus delta x upon x. So v is equal to 9 plus minus 0.9 centimeter square. So delta v is 0.9. Next, to compute delta y square upon y square, it is equal to 2 into 0.6 upon 3, it is equal to 0.4. So delta z is equal to 0.9 plus 3.6, it is equal to 4.5 centimeter square, and it is approximately equal to 4. So z is equal to 18 is the central value and 4 is the error involved for the average error. But if we are taking the standard deviation, then the error involved is almost same, it is equal to 3.7 and it is approximately equal to 4. Next, we can take the error with the, like for the trigonometric function z is equal to sin x. So we can easily find out delta z is equal to delta of sin x, and this is equal to sin of x plus delta x minus sin of x, and for the cos of x, delta z is equal to delta of cos x, and it is equal to cos of x plus delta x or x minus delta x minus cos of x. So next is one example involved for this measurement. So we come to the next example, accuracy example. Suppose 24.44 milligram iron Fe is an ore standard. So the data involved here, it is written 24.39, 24.43, 24.41, 24.45. While the error in this measurement we can easily calculate by taking the first the mean of all these measurement. So x bar is equal to the sum of all these measurement divided by 4, it is 24.42, while the accurate value is 24.44. So the error in each measurement we can calculate 24.39 minus 24.44, it is equal to minus 0.05. So we can easily calculate the rest of error like minus 0.01, minus 0.03 and 0.01. So the sum of all these error, it will give us minus 0.08. So the bias is 24.42, mean value minus the actual value, it is given 24.44. So it is equal to minus 0.02, and the relative bias, it is equal to this bias divided by the actual value into 100. Absolute and relative uncertainty. Suppose we can measure the volume of a solution to 0.010 ml. Is that good or not? It depends upon the central value. If central value is more, then this is very good. If the central value is less, then this is very bad. So the uncertainty involved for the first case is 0.01 divided by 1000, it is equal to plus minus 1 into 10 raised to power minus 5, while for the case 2, it is the error, it is equal to plus minus 0.5. So if the central value is more, then the error, if the error is less, then that quantity is fine. But if the central value is less and error is more, then that measurement is not fine. Next, we can easily find out the relative uncertainty in terms of the percentage error, parts per thousand, parts per million, with multiplying by 1000, by 100, in the first case, 1000 in the second case, 10 raised to power 6 in the third case. Next we can calculate the percentage uncertainty is equal to absolute uncertainty divided by mean value into 100. It is equal to 0.5 divided by 8 into 100. It is equal to 6.25%. So next conclusion, error is mainly the difference of actual value and true value of that physical quantity. Error is very important while doing an experiment or while taking any measurement. It is mainly error which tells us how precisely and accurately we can measure a physical quantity. There are number of sources for the error like systematic, environmental condition, random error, detection efficiency, faulty instrument, etc. Thank you.